Good afternoon. We'll discuss the today we'll discuss the sequence impedances of symmetrical circuit. So basically in previous topics we have discussed only the symmetrical components of voltages and currents. Now for each symmetrical component, that means each sequence, positive sequence, negative sequence and zero sequence components having their own impedance. So basically what is the impedance? Yes? What is the impedance? Yes? Basically, what is the impedance?
It
So,
restricts the
restrict the flow.
impedance
Yes, restrict the
flow
flow
of
of
current.
AC current. Right? So,
Yes,
for each sequence component, like positive sequence component, negative sequence component, and zero sequence component, having their own impedance. So the magnitude of this impedance depend on the which equipment you are using in the power system. Example, there is a different impedance for transformer and there is a different impedance for transmission lines. There is a different impedance for generators. So each equipment poses or each equipment encounters different impedances. Either it is positive sequence impedance, negative sequence impedance, zero sequence impedance. Some of the components having their own impedances. It is not similar that the positive sequence component of transmission line should have the same impedance of positive sequence component of generator. It is not like that. The impedance depends on the your current and the windings which you are using. That is different matter. But what I mean to say is here, whatever the impedance encountered by this sequential component, positive, negative, zero sequence, the magnitude of this impedance depend on the type of the equipments which you are using in the power system. Example, if your generator, transmission line, transformers, all these equipments are not having the same impedance. Different equipments in power system having different impedances. No. So basically, for a brief, this sequence impedance will be divided by three, will be classified into three groups. However, you classified for sequential component, the same thing here also it will be classified as three sequence impedances. One is positive sequence impedance, negative sequence impedance, and zero sequence impedance. We will see in detail this in the next coming lecture. But in brief, I will explain what is positive sequence impedance, negative sequence impedance, and zero sequence impedance. So the impedance of a circuit element only when positive sequence current alone are flowing in the circuit, that is called positive sequence impedance. That means only there is an IA1, that means only when positive sequence are currents flowing in the circuit, only that positive sequence current, then we call it is a positive sequence impedance. Negative sequence impedance means only the negative sequence components of currents are flowing, then it is called negative sequence component. Then the zero sequence negative sequence impedance. Then zero sequence impedance means only zero sequence components of current flowing in the circuit, that we call it as a zero sequence impedance. So basically only IA naught is flowing in the circuit means it is a zero sequence impedance. If IA1 is flowing in the circuit means it is a positive sequence impedance. Then how about IA2? Yes, if only IA2 flows, it is negative sequence impedance. So there is a small derivation will be there, how this positive sequence components will be, or how this symmetrical circuit, how it will be there, how your phase, that means this sequential component of voltages will be relating with the sequential component of currents, that we will see here. Now, before going to this, just we'll give a brief introduction. Now, what is symmetrical circuit? Yes, anyone, please? What is symmetrical circuit? Yes. What is symmetrical circuit? Symmetrical and unsymmetrical. Yes.
Same magnitude and phase.
Yes. So it should be having the same magnitude and phase. So that for symmetrical circuit, what is this impedances? In your syllabus also, it will be there for symmetrical circuit only. Now, consider a three-phase symmetrical circuit. Consider a three-phase circuit which is symmetrical. That means your RYB or ABC will be same magnitude and the same figure. Let you consider this. Yes. Let IA be one phase. Sorry, IA current flowing in one phase, IB current flowing in another phase, IC current flowing in another phase. Let you assume this is an X phase or RYB, this is an Y and this is an Z. Or let you say this is A only, you will confuse here. This is A phase, B phase and C phase. Just is C phase. Now let you assume that the current flowing in the A phase is IA and the current flowing in B phase is IB and current flowing in C phase is IC. Now for each and every line there is an impedance that you see here they have been given. Let IA, IB, IC are the line currents and these currents return through the neutral impedance. Now Z is the impedance of the phase A, Z is the impedance of phase B and this Z is the impedance of IC, that is phase C. IA, IB, IC are the line currents. Now all these line currents meeting at this point. All these line currents are meeting at this point. Just I will name it is an IN. So now can you tell what is IN? What is IN according to the KCL? Yes? What is IN? IN? Can you tell? This is my central point neutral. So these IA, IB, IC are the incoming currents and IN is my outgoing current. Now, what KCL states?
IN equal to IA plus IB.
IN equals to IA plus IB plus IC. Now, what is the voltage? Now, we will find the voltage drop across the phase A, phase B, phase C. Now, what is voltage drop? How we will give voltage drop? So, here for the voltage drop is, for phase A, it is
Current.
I current into impedance. V equals to IZ, right? So, voltage impedance here, this one and this one, IAZ and here plus INZ. From here to here we need to, because we are considering symmetrical. If it is an unsymmetrical, it is different scenario. Now for here to here, what is the impedance for phase A? From here to here, it is just like this. Yes. Yes. Now consider the circuit like this, right? One more. This is my R. Consider it is an RA and this is Rn. So now this is my IA. This is also my IA. Consider like this. Now, yes. Now how we will find V1 and V2 here? Yes? How we will find the voltage drop in V1 and V2?
So screen is not visible.
Screen is not visible. Ayyo. 1 minute. Yes, now it is visible.
Yes, sir.
Now how we will find the voltage drop across V1 and V2? See here, this is just a circuit. So RA is my resistance and Rn is other resistance. The current flowing here it is IA, here also it is IA. Now if I want to find the voltage drop across this resistor and if I want to find the voltage drop across this resistor, how we will find?
IA into RA.
The voltage drop across V1 is IA into RA and the voltage drop across V2 is IA into Rn, right?
RA.
Yes. Similarly, here also the same. Instead of resistance, we will take it is an impedance. Now, if I want to know the voltage drop in the phase A, so it is IA into Z plus IN into Zn, right? The voltage drop here and the voltage drop here I need to find. So the voltage drop here it is IA into Z. Here the voltage drop into IN into Z. Similarly, what is the voltage drop in VB? In phase B, assume that it is a symmetrical circuit. Yes? What is the voltage drop in phase B? Yes? Connected or? Yes. What is the voltage drop in phase B? Anusha?
So IB plus Z plus IN plus Zn.
No. IB into Z plus IN into Zn. Right? It is not IB plus Z.
Yes, sir. Yes, sir.
IB into Z.
Sorry, IB into Z.
IB into Z plus IN into
Plus
Zn.
IN into Z.
Similarly for IC. Similarly for phase C.
IC into Z plus IN.
IC into Z, IN plus IC into Z plus IN into Zn. Right? So same thing here had been given. The voltage drop are computed as follows for the symmetrical circuit. Now VA equals to IA plus IAZ plus IN into Zn. Now VA equals to IAZ, let it be same. What is now IN? What is IN? Yes? IN it is IA plus IB plus IC, right? This is my IN. IN is the combination of or the sum of the phase currents, right? So instead of IN, I will write IA plus IB plus IC. This I will write into Zn. Now, so what will happen? You multiply this IA into Zn plus IB into Zn plus IC into Zn you will get, and here IA Z you will get. So take common as IA, then you will get Z plus Zn, IB plus IC, Zn. Take Zn as a common, IB plus IC, Zn. Now overall what it becomes? VA equals to IA Z plus Zn, IB into Zn plus IC into Zn. Multiply this and this and this and this. Now, similarly VB, only the change is here. Instead of IA, I will get IB here. So wherever the ZD will be there, Z plus Zn you need to write. So here for VB equals to IA Z1 plus IB Z plus Zn plus IC into Zn. Similarly for VC, it is an IA into Zn plus IB into Zn plus IC Z plus Zn. Here you can see here you can see the only change part is here. For phase A, you will get IA Z plus Zn. For phase B, you will get IB Z plus Zn. For phase C, IC plus Z plus Z1. Now, I will put this in the matrix form. So, if I put in the matrix form, your LHS side it becomes VA, VB, VC. This VA, VB, VC. And your this RHS it becomes Z plus Zn, 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 again Zn, Z plus Zn, Zn again. So the diagonal elements will be the same for this Z plus Zn, Z plus Zn, Z plus, and upper and lower diagonal elements will be Zn. And here we will need to multiply IA, IB, IC. The same Z plus Zn into IA, Zn into IB, Zn into IC for VA. For VB, it is Zn into IA, Z plus Zn into IB and Zn into IC. For VC, it is my Zn into IA, Zn into IB, Z plus Zn into IC. Now, what is VA, VB, VC? These are my phase voltages. Now, if I need to represent this in terms of symmetrical components, we have derived in the second class only. If I want to represent this in terms of symmetrical components, you know that VA, VB, VC, it can be written as 1, 1, 1, 1 A square A, 1 A square. This is phase voltages in terms of symmetrical components we are representing. Now this whole term becomes this. Yes. This is equal to this. Now this I written in the form of like this. 1 into 1 this is. Now keep this as common. Yes. Keep this as a common. Now Z plus Zn, 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 the same common. Here again IA, IB, IC. I will write my line currents in terms of my symmetrical components. So if I write symmetrical components IA, IB, IC, right? Then I will get this. The term, yes. I can represent IA, IB, IC in this form. 1, 1, 1, 1 A square, this. Now, you need to multiply all the terms. Now, let you take VA, VA0, VA1, VA2. So, what is the symmetrical component here? Symmetrical components had been given. So, you have derived this VA0, VA1, VA2 equals to 1 by 3, 1, 1, 1. This you have derived. These symmetrical components in terms of phase voltages. This. Now, so 1 by 3, the 1 into 1 into 1, sorry, 1, 1, 1, 1 A square, 1 A square, A. Now, what is VABC? Here, this is your VABC. So, VABC is Z plus Zn, 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 this matrix. So, you substitute this value here. Yes. Substitute this value, VA, VB, VC. Substitute this value here. Now you will get this Z plus. Similarly, substitute for IA value, IA, IB, IC, whatever the value is there, that value you substitute here. IA, IB, IC equals to 1 into 1 A square this. So you will get. So after all this you multiply. How you will multiply? Your rows and columns should be matched. So this and this should be matched. So first you multiply these two, then afterwards you can multiply the remaining answer. Now after multiplication of these two you will get this answer. You can go through this, or I will send the PDF. You can go through this. The derivation had been given here. In textbook it has been given directly, so I derived here. Yes. Now 1 by 3. So 1 by 3 is a common here. Now z plus zn, you will get the answer of multiplication of these two. Now once you get the answer, again multiply with this. So finally you will get z plus 3zn, z plus 3zn. So the same z plus 3zn, z a square z. Similarly you will get z a square az. Now what you need to do, you multiply these two. This and this. You multiply these two terms, you will get finally 3z plus 9z and zc 1 plus a square, like that. So finally you will get this answer after simplification. Yes, any doubt? Yes. So once you get simplification, then z plus 3z and z, like 3 you need to take as a common. So this 3 and this 3 will get cancelled. This 3 and this 3 will get cancelled. So you will get z plus 3zn, z as a diagonal elements, and upper and lower element will be 0. Here my IA naught, IA1, IA2 keep like this. Now what will become the above matrix? VA naught becomes, can anybody tell? VA naught is? Yes? What is VA naught here?
Z plus 3Z
Z plus 3Z
into IA naught.
IA naught. Now what is VA1? What is
Z
V?
into I,
Yes?
Z into I2.
Z into IA1. What is VA2? Z into IA2.
Z into I2.
The same thing, the same here had been given. So VA naught equals to Z plus 3Zn into IA naught, VA1 Z1 into IA1, VA2 Z into IA2. So here Z equals to Z1 equals to Z2. It had been given here. This is not the case for all the situation. That I will tell when it will be equal, when it will not be equal. Now, when VA naught equals to Z naught into IA naught. Now, let me say VA naught equals to Z naught into IA naught for zero sequence impedances. Now, what is my IA naught? Usually, Z naught, zero sequence impedance, we can see here Z plus 3Zn. So here what they are written, Z naught equals to Z plus 3Zn. So they have been designated as Z naught as Z plus 3Zn. So now Z1 is Z1 equals to negative sequence impedance equals to Z. So that means Z equals to Z1 equals to Z2. That means here total, if I say sequence impedance, my positive sequence and negative sequence impedances are equal. But my zero sequence impedances are not equal to positive sequence impedance and negative sequence impedance. In many of the cases, your positive and negative sequences impedances will be equal, but zero sequence impedances will be almost, it is not almost, always greater than your positive and negative sequence impedances. So this is not all the conditions that positive and negative sequence impedances will be equal. It depends on the whether transformer, or it depends on the line, and depends on the generator, which equipment you are using. But 90% positive and negative sequence will be treating as equal only. That we will discuss later. Now we'll take a small problem. So there is an across a star connected symmetrical impedances load of 100 ohms will be there. There is a star connection. Yes. There is a star connection. So what he had been given, there is an impedance of 10 ohms he had been given. Of each phase, they had been given 10 ohms. Here 10 ohm. Here 10 ohm, here 10 ohm, and here also 10 ohms. So impedance value they had been given. And a neutral impedances of 3.33, because 10 by 3 it is 3.33 only. An unbalanced three-phase supply. That means whatever the supply is here, it is not balanced. There is an unbalanced supply will be there. So here they had been given VA, VB and VC. These are my phase voltages. Now VA 220 at an angle 0, VB 220 at an angle 110 degree, and VC 180 at an angle minus 110. This has been given. So what we need to do is determine the line currents using sequential components. I need to find line currents. What is my IA? What is my IB? What is my IB? And what is my IC? I need to find these currents. So the line current here, IA, IB, IC, I need to find the line current. Yes. So similarly, had been given here. This I will erase. And so VA, VB, VC had been given. VA is 220 at an 0, VB is 220 at an, VC is 180 at an angle minus 110. So I need to find what is the current here. The current here. If I make this, I need to find the current from here, the current from here, the current from here. The line currents you need to find. Now IA, IB, IC. Right. So how we will write IA as in terms of sequential components? IA0 plus IA1 plus IA2. How we will write IB? It is IA0 plus A square IA1 plus A into IA2. IC, how we will write IA0 plus A into IA1 plus A square into IA2. This you know. Now we have seen the from previous derivation Z equals to Z1 equals to Z2. So that means my impedances Z equals to positive sequence and negative sequence impedances are same. But what is my zero sequence impedance? Zero sequence impedances is Z plus 3Zn. Zn is equivalent. It is an impedance in a star connected system at neutral. If it is a star connected, you need to, if all the impedances are same, If it is a star connected, you need to divide by √3. If it is a delta connected, if all the impedances are same, you need to multiply by 3. It is an equivalent impedance, I can say. However, you will do in the network the same thing here. So Z0 equals to 20 ohms. 10 plus 3.33 into 3. So it is 20 ohms. Now, let IA, IB, IC are the line currents and is given by using the symmetrical components. So IA, as I said, IA0 plus IA1, IA2, this from the symmetrical components in terms of line currents. This you know. IA0 plus A into IA1 plus A square into IA. Now, basically what is I? It is voltage by impedance. It is simple. From the Ohm's law only we will find this. So IA0 equals to, I can write VA0 by Z0. IA1 is VA1 by Z1. IA2 is VA2 by Z2. Now, I want to find VA, what if I know VA0, VA1, Z, because Z we know. If I know VA0, VA1, VA2, that is sequential components, then I can get IA0, IA1, IA2. If I get IA0, IA1, IA2, I will get IA, IB, IC. It is a reverse operation. So try to find VA0, VA1 and VA2. Now, VA0 will be find 1 by 3 VA plus VB plus VC, and VA1 will be find through 1 by 3 VA plus AVB, applying the same formula. So 1 by 3, so VA had been given 220 at an 0, VB had been given 220 at an angle 110, and VC had been given at 180 at an angle minus 110. Now, similarly for VA1, so apply the formula this, A equals to 120 degree, A square equals to 240 square. So if you multiply the two vectors, then your magnitude will be multiplied and your phase angles will be added. So here A square means it is 1 at an angle 240 and A means what? 1 at an 120. Here, so VA1 is 220 plus at an angle 0, this is reference, and here it is A square, it is VA1 A into VB. So A is value what? 1 at an 120 and VB is given 220 at an angle 110. So this value and this will be multiplied, and this will and this will be added. Angles will be added, magnitudes will be multiplied. Similarly here also the same. So you will get VA1, VA2 the similar value. VA1 you will get 9.56 at an angle minus 147, and VA2 you will get 198.7 at an angle minus 0.33. Now from this you will get VA0, VA1, VA2. So find IA0, IA1, IA2. So IA0 you will get 30.65 divided by 20 because it is Z0. Z0 is Z plus 3Zn. Similarly IA1, from this you will get IA0, IA1, IA2. So once you get IA0, IA1, IA2, so you will get the values of IA0, IA1, IA2. So then, now once you get the values of IA0, IA1, IA2, apply in the IA value. So what is IA? It is similarly IA equals to IA0 plus IA1 plus IA2, these values. Yes, these values. IA equals to IA0 plus IA1 plus IA2. IB equals to IA0 plus A square IA1 plus A into IA2. So the same value we are substituting that. So finally you will get IA value as 20.5 here, and IB is 20.27 at an angle 114, and IC equals to 18.85 at an angle minus 113. So only one problem is there on this. So if you perfect this, maximum times this only will be asking. Now the next topic is prove that. This is very important. You can make mark as an important. I also marked as important. And before going to this, which textbook you are referring? Yes? Which textbook you are referring?
Neelkant.
Oh, Neelkant you are referring. Okay. The same. It is good for the problems, and meanwhile refer this also. Which book? Kotari, Modern Power System Analysis. That also good. And problems more in many times. So they will be giving on Neelkantan book only. Right? Some of the problems are common in Neelkantan and DP Kotari. First, you need to concentrate on that, because those who are taking the will take the question paper. They will not refer this Neelkantan. They will refer DP Kotari only, and moreover, they will prefer old question papers. Right? Now, so here what is it's most important, because in many question papers this question had been asking revisely. They will be asking at every time, at once in a year, at or every time, but most important question it is. So prove that a three-phase symmetrical wound generator generates only the positive sequence component of voltages. That means my symmetrical wound, the generator generates only the positive sequence component of voltages. The negative sequence component and zero sequence components are zero. Only the generator generates the positive sequence component of voltages. That's how we will see. See, let us assume this. It is the generator is connected in star. So A, B, C are my terminal voltages. This A, B, C are my terminal voltages of generator. Now EA, EB, EC are my generated voltages of each phase. EA is generated at A phase, and EB is generated at B phase, and EC is generated at phase C. Now that EA, EB, EC are the induced voltages or voltages of a three phase. Now this B phase induces EB, C phase induces EC, and A phase induces EA. Now, as I said, since the windings are symmetrical, the induced EMFs are perfectly balanced. That means my EMFs are balanced. That is, AB, BC and CA will be having the same line voltages, and it is displaced by 120 degree. Now, so how we will write what in terms in the present? Let the phase sequence is A, B, C. Right? Let the phase sequence is A, B, C. Phase sequence means, like I will write, no, this is A, this is B, and this is C. Now it is rotating in anti-clockwise direction. Now let us say phase sequence means EA, EB, EC, which is equal to VP, that is my phase voltages. Now let you say, how can I write EB? Yes? How can I write EB? So let you assume this EA, EB, yes, EC, EC. And now, if I want to represent EB in terms of EA, how will you write? Yes? Anusha? Yes? Anusha, Kapil?
So,
Now, if I want to represent EB, how will you represent in terms of EA? It is rotating in anti-clockwise direction.
A square into A.
Yes? A square into EA.
Sir,
Right?
EA.
Now, what is EA? EA equals to EB equals to EC. Right? I can represent EA as VP. Now, in terms of VP, you tell EB equals to VP at an angle 240, right? See, here I assumed as EA equals to EB equals to EC. That combined name I had been given VP. Let you consider this EA as in my reference at an 0 degree. Now, if I want to write EB in terms of EA, how can I write? EB equals to EA into 240 or EA into A square, right? So EA I represented as like VP. Now EB equals to my A square into EA. The same thing here had been given. EB equals to VP at an 240. This you can represent minus 120 also. You don't confuse with this. Let you go for this only. Now, similarly relate for EC. How you will write EC in terms of EA? Yes?
A into
Huh.
VA.
Yes? A into
A into E. Sir,
EA.
in terms of VA.
Yeah. So EC equals to A into VP, or you can write EA also. Right? The same thing. A, what is A? It is 120 degree. 1 at an angle 120 degree. So EC equals to VP at an angle 120 degree. Now, hence the sequence components of voltages are EA naught is 1 by 3 EA plus EB plus EC. This you know. And EA naught equals to 1 by 3 VP at an angle 0. This is in EA. I am representing in terms of EA. So it is VP at minus 120. So this 240 you can write 120 also, and this minus 240 you can write 120 also, no issue. So substitute this value, or else if you write this value is also no issue. So EA naught equals to 1 by 3 VP plus 1 plus, after substituting all this, you will get EA is 1 by 3 into 0. You can substitute and check. And similarly EA1, it is 1 by 3 EA plus A into EB plus A square into EC. Apply that EB value and EC value here, whatever you will get. So that you will get is, after substituting all the values, you will get EA1 equals to VP. So that is equals to EA. Similarly for EA2, EA plus A square EB plus AEC, you substitute for the values of EC and EB, whereas EB equals to 1 at an angle 240 and EC equals to 1 at an angle 120. Now finally EA2 you will get the 0. So what we need to prove is that the generator, prove that a three-phase symmetrical wound generator generates only the positive sequence component of voltages. Now here in this case EA naught is 0, EA1 is EA and EA2 is 0. Only the positive sequence component will be present. The other two components will be 0. So that we need to prove it. That we have proved here. So sequence network of the power system we'll discuss later.